Um, okay, good evening, everyone. We'll be starting the workshop now. I'm Tejas, and I'll be leading a workshop today on understanding neural networks and exploring its applications and in particular cryptocurrencies. But before I proceed any further, I would like to give a short disclaimer, which is that the workshop is intended for educational purposes only, with a particular focus on understanding the technology of neural networks. And we do not and have not considered any specific investment objective, financial situation, or goals of any person when compiling the information for this workshop. And the workshop does not condone nor promote investment in cryptocurrencies, nor does it claim to offer expertise in predicting the prices of cryptocurrencies for investment purposes. So now that we've got that out of the way, I think we can start. So today we'll primarily be building a model to like forecast cryptocurrencies using neural nets later on, and feel free to code along later because we'll be getting hands-on, and there's no setup required because we'll be using Google Colab, which I'll be getting into later. But before we get hands-on, I would like to give you a brief introduction of some important topics related to the workshop today. So what is deep learning? Deep learning is essentially a class of machine learning algorithms that uses multiple layers to progressively extract higher level features from the raw input. So that may sound a little complicated, but you'll definitely get a clearer understanding later. But it's essentially a subset of artificial intelligence and machine learning, where AI basically mimics human intelligence and the behavioral patterns of humans, whereas machine learning is essentially a technique by which computers can learn from data without using a complex set of different rules. And now I'll be showing you what neural networks exactly are. I'll first give you a brief overview just for now, and later, hopefully, once we get hands-on, you'll get a better understanding. But the name and the structure of neural networks are mainly inspired by the human brain, mimicking the way that neurons in our brain signal to one another and how our brain works. So essentially, each node or artificial neuron connects to another one and has an associated weight and threshold. And if the output of any individual node is above the specified threshold that is associated with the neuron, then the node is activated by sending data to the next layer of the network. Otherwise, no data is passed along to the next layer of the network. And that may sound a little overwhelming, but I'll try explaining it further. So there are basically three kinds of layers over here. There's an input layer, there's a hidden layer, and the output layer. So here the input layer is the green portion of it, and the hidden layer is these blue set of neurons that you see here, and finally there's the output layer. So over here, although there's only one hidden layer, neural networks generally have more hidden layers. And let me give you an example of where these are used. Over here, they could also be used for let's say image recognition. And in an image recognition application for let's say detecting a face. So the raw input is essentially a matrix of pixels. That's because when you take a picture, there's the red, green, blue values, which are usually which is on a numerical scale. And those are fed into the neural network in the form of matrices. And then, like, for example, the first hidden layer may get the pixels and it could encode like the edges. And then the second layer, for example, could compose and encode the arrangement of the edges. And the third layer may encode the nose and the eyes. And then lastly, the fourth layer may recognize the image that contains the face. But more importantly, deep learning can learn which features to optimally place in which level on its own. So, and a neural network also acts as a black box in the sense that while it can approximate a function and everything, but studying a neural net structure won't give you any insights on the structure of the function being approximated. So, I mean, I've explained quite a bit, but if you don't completely understand, it should become clearer later. And additionally, we'll also be providing you with some learning resources at the end of the workshop if you're keen on learning more. So yeah, so today we'll also be using some toolkits and libraries. So I hope like most of you must be familiar with like Python and all of that, and some of you may even be familiar with some of these libraries. So we won't be going too in depth into these libraries. We'll be using them very briefly, not we won't be using any complex functions of them or anything. But so let me start off by saying that Pandas, a lot of you may have heard of it. It's an extremely popular like Python library that's used for data manipulation and analysis, and in particular, it offers data structures and operations for manipulating numerical tables of data and time series data as well. And time series data is what we'll be getting into later when we're forecasting the prices of cryptocurrencies. And over here, NumPy is another Python library that's used to operate on multi-dimensional arrays and matrices and basically manipulating them. And matplotlib is a plotting library, which is essential for creating data visualizations. And it's also built on the basis of NumPy arrays. And lastly, okay, no, scikit-learn is a machine learning library, but over here we'll be using a bit of it for like some data preparation as well. But lastly, Keras is the library that provides us with the neural network functions, and essentially it's a library for developing and evaluating deep learning models. But we won't be going too in depth into the libraries, but we'll be showing you how various functions and basic functions are called and how we can use them. But if you'd like to know more, there are lots of resources online, and it's not very difficult to like go more in depth by learning more of it. And hopefully the basis that we form in the workshop could act as a stepping stone for further exploration of any of these libraries or topics that you might be interested in. But anyways, now I'd like to get started with the coding part, and you could feel free to code along as well if you don't, because it doesn't require any setup or installation, because we'll be using Google Colab. And Google Colab is essentially a Jupyter notebook that doesn't require any setup, and it's completely free. And it's great for running deep learning tasks as well. But if you haven't heard of like what Jupyter notebooks are, they're basically they let you run cells of code instead of all of it at once, and it's extremely useful in cases like deep learning. So I'll get started with sharing the coding part. So give me 1 sec. And if any of you have questions, you can leave them in the chat, and hopefully we'll be able to get to them by the end of it. I've sent a link of a Google Colab in the chat that that you can go through, that we'll mostly be going through as well. But you could also create a new notebook by yourself and start coding if you want, and use that as a reference. But anyways, I'll be sharing my screen in a moment. Just 1 sec. Yeah. Can you guys see my screen? Okay. Okay, cool. You got it. So first part we'll be getting into the data preparation and cleaning essentially, but later on we'll get into the main deep learning part. But for the data set that we'll be using today, it's from the AlphaVantage API. And AlphaVantage is an API that essentially provides financial market data, and they give you things like daily stock prices, cryptocurrency prices, forex data, and even provide you with like additional metrics for different asset classes. But we'll mainly be working with the crypto data. In fact, I came across the API when I took Introduction to Data Science and AI last semester, and the professor taught us about it. So if you do take that sometime, then you might be working with it as well. But anyway, so wait, let me just send. Yeah, okay. So there's a link in the chat if you wanna look into it. But the advantage of using an API like this one is mainly that they can provide real-time data. So you can sign up for an API key, and it's completely free and easy. So if you just go to the link in the chat, and then you can click on get your free API key today. And you're a student, whatever your organization email, just once you fill in everything, and you'll hopefully get an API key. And I've already done it, so I'm not going to do it again, but I'll give you like a couple of minutes just to try it out. Okay. And let me know if you're facing any issues with getting a key. But okay, so I think I'll assume that everyone's got a key if you're following along and coding. So you can just copy the key and maybe like paste it like somewhere else for now, like in like Notepad or something like that. So we'll be using it later on. Okay, so you can just go to Google and search up Google Colab if you're interested in coding along. But I've also sent a link to basically a notebook for reference that we'll be using today. But you don't have to look at that right now. You could maybe start coding along, and if you can't follow anything, you could check out the notebook, or you could ask me or anything if you have any questions. Okay, so I'll get started here. So to basically use the AlphaVantage API in Google Colab, we'll have to install the package. So this is essentially a command to install the AlphaVantage packages that we'll be using. Okay, and so if I rerun it, it'll probably take like a couple of seconds, but okay. So over here, we're in the next line of cell of code, we're essentially importing the libraries that we'll be using now. So I mentioned like Pandas, NumPy, and Matplotlib. And over here, we're using the AlphaVantage library that we just installed to extract cryptocurrency data over here. So in the next cell, where we create an object that we're using, a cryptocurrency object, and we're using it to call the get digital currency function. But when you're creating the object, just remember, so over here, I haven't really mentioned the API key because I wouldn't want, for security reasons, that it's not advisable to be showing everyone the API key. So, but you could, if you copied it earlier, you could just paste it directly here. But I'm using a text file, so you won't be able to see the exact key. But anyways. Yeah. So once you've got the key, and here the output format is pandas because we'll mainly be using pandas to play with the data and with the data tables and everything. And what this essentially does is you're using the cryptocurrency object that you have to get digital currency daily, which basically gives you the value of the crypto. And over here, BTC is the ticker of like Bitcoins, as you can see, and this is the market. And if over here, if I just type in crypto data, and if I run it now, okay, wait, give me a second. Oh, okay. Yeah, so this gives you a data frame. It shows you a data frame of like a bunch of metrics over here about like Bitcoin, and this is over here the closing value in US dollars is given, which we'll mostly be using. But so what a data frame is it's just a data structure that contains like columns and rows, and you can operate on it and get like bunch of things with it, and it's useful for like playing around with data basically. Yeah, and if you want, you could even like try something like Ethereum, and it should give you the values for that as well. And so we'll mostly be using the closing values. So I'll just change it back to Bitcoin. Okay. Yeah. So this is the column. So 4b.close USD. That's the column that we want because it contains the closing values. And when you call the API, essentially it returns the data for the past 1,000 days. So yeah, we basically have 1,000 rows because with each one representing a day. Then if I run the next cell, you'll see a plot of the values of Bitcoin. So to extract a column from the data frame, what we basically did was crypto data is the data frame, and then the 4b.close USD, that's the name of the column. So what crypto data 4b.close USD, this basically extracted the column from the data frame. And then dot plot is basically it's a matplotlib function that plots it. So for example, if I show you if I just print out crypto, oh yeah, so okay, never mind, I've done it here. So over here, if I run this crypto data 4b.close USD, so we're putting it in another data frame, and then if you print out the data frame, it shows you a bunch of these values, which are the closing values. And I'd also like to show you like the type of the data of what we're working with. So instead of printing the data frame itself, I'm just showing the type of the data of crypto data, and it shows that it's a data frame, a pandas data frame to be exact. So anyways. Okay, and then so this is the title of the graph that we're plotting, and then grid just displays the grid like these lines over here. and then show finally plots the graph itself. Okay. Then this is like 100 rows, so it doesn't like display everything. So it mostly just like displays like the top few and then the bottom few. And then this is another function that we're using here, dot describe. This is really not essential for us to like to do the deep learning portion, but over here I've used this to basically give us like insights into like what kind of data we're dealing with. So it gives us a bunch of like statistics. So for instance, we get the count is basically the number of values that we have, which, as I mentioned, which is the closing value of Bitcoin for the last 1,000 days. And mean is the average. And then this is the standard deviation. And then the minimum value in the last 1,000 days. And then the lower quartile, the median, the upper quartile, and finally the maximum value, which is like 60K. But the problem with over here with the data frame that we're dealing with, which has the closing values, is that you may have noticed that the first index of the data frame gives us the most recent date and the price of the closing value of Bitcoin on that date. But since it would be easier if we instead had the first date that we were dealing with as the first index, this essentially it reverses the order of the rows, and we're putting it in a separate data frame called Bitcoin order DF. So if I run this, then you can see that the first date that we're dealing with over here is the 9th of December in 2018. So, and the closing value of Bitcoin on that day was $3,500 ish. And then over here, this is the latest index, which is the 3rd of September. So, yeah. Okay, now we're importing more libraries here that we'll be using for like deep learning. And then some of the scikit-learn libraries also that we'll be using. And then we'll be using them later, so don't worry about them right now. So you could just import them. Okay, so over here we're getting these values, and then we're assigning it to a new variable called dataset. And over here, what we're doing is we reshape it into a 2-dimensional array, so that it's because that's basically what the Keras deep learning models deal with. So once you're done doing that as well, then float 32 just refers to a floating point value, which I'm sure most of you are familiar with. And then in this line, we use min-max scaler, which we imported from the scikit-learn library to basically normalize the data and make the values between 0 and 1, because like computers are better with manipulating and predicting data when it's between like 0 and 1, when it's normalized per se. So that's basically what this code block here does. And when we're predicting the prices of cryptocurrencies, so we'll be using a portion of the data to train the models, and then another portion to test the models. So over here we're splitting up the data into like 2/3 and 1/3. So we're using the first 2/3 of the data for training it, and then the second the last third of the data for testing it. So that's basically what this code block does. And then if I print out the test and train size, it shows us that the train size is 660 and the test size is 340. And since we're dealing with 1000 values, we know that this is probably right. And so since we're doing time series forecasting, how the neural networks works is that it essentially uses previous values of the data to predict like future values. So that's what we're doing over here. So where we create a data set where the closing value of the cryptocurrency at any given time is X, and the closing value at the next time period is Y, where the sequence size over here, it's a variable that is basically the number of previous steps that's used as an input variable to predict the future values. So that's what this function does over here, and we'll be calling this function later on. Okay, yeah. So that's what sequence size over here is. We could change it to anything actually. So it could even be like 20 or 30, but and larger sequences sometimes improve forecasting, but not always. Depends on the kind of data that you're dealing with and what you're trying to predict. So over here we're predicting cryptocurrency data, but you could do something like this for you can even do it for like stock prices per se, and then for time series forecasting could also be done on like multiplying like bacteria if you have data for that, like how much bacteria will be there later and that kind of stuff. So yeah, that's what we do over here, where we get the training and the test set, and then we use this function that we've defined to create the data as previously mentioned. And then if I print out the shape of the training set and the test set, we see that it's 649 by 10 and 329 by 10, and 10 over here is the sequence size. So do note that over here we're using Lstm neural networks, which are a kind of recurrent neural networks, which can not only process like a single data point, like an image, but it can also process like entire sequences of data, which so it can be used in say like speech or video. And over here a sequence of data is essentially the previous closing values of Bitcoin. So this is why they're like well suited for making predictions in the time series data. And over here we're using a univariate Lstm, which means that like as I mentioned, there's it's predicting the future values based on the previous values. So it's just one kind of variable that it's taking into consideration. So which is why I'd also like to say that this is just mostly like an introduction into how you can use this for time series forecasting and stuff. And this is not necessarily the most sophisticated model. So, and in some cases, people do say that that LSTMs shouldn't be like, they aren't the best at like predicting like cryptocurrency prices, because given how volatile crypto is right now, there are not a lot of viable methods, and in fact not a lot of research has been done into it either. So yeah, for predicting like cryptocurrency data in particular, given the volatility. But anyways, so these are in this cell we basically define the model that we're using. So these two lines basically reshape the train and the test data that to basically form a layer of the neural networks that it's fed in as an input layer. So as I previously mentioned, there's one input layer that we have, and then there are multiple hidden layers, and then there's an output layer. So these serve as the input layer. And here we're adding the conv LSTM2D, which is basically the convolutional univariate LSTM. So, and we imported this from Keras that I mentioned, which is the deep learning library that we're using here. Which is basically the size of the input. And then these two layers over here are the dense layers, which are basically the hidden layers that progressively extract value from the previous input layers. And then here we're finally compiling the model. And optimizer over here it says Adam, which is basically just an optimization algorithm that I really don't want to get too deep and technical into, but you could definitely check it out and in the documentation. And there are a bunch of other optimizers as well, and we're just using one of these over here. So this should mainly just serve as a brief introduction into this and as a baseline, and you could definitely explore more by reading the documentation on the official website. And then again, you could check out different loss functions as well, but over here we've used mean squared error, which is basically here the loss is calculated as the squared differences between the actual and the predicted values of cryptocurrency data. So the purpose of these loss functions is to basically compute the quantity that a model should seek to minimize during training. So what the model should focus on minimizing while training the model. So here it tries to minimize the error between the predicted and the actual values that's calculated by the mean squared error. And model.summary basically prints out the overview of the model that we've defined and what we'll be using. But anyways, I don't want to get too in depth into it, but if you haven't understood or if it feels overwhelming, especially this side of the code, you should definitely explore more of it later on, because this is just a baseline, and I obviously can't cover the every detail of it within a short time period. But okay, anyways, moving on to the next cell. What we do over here is we're training the model. So over here we use model.fit, which is a function that's used to train the model. And here epochs refers to the cycles that it goes through the number of cycles that it goes through the full training set. And verbose it isn't too important, but it just displays it basically depicts how the progress of a training is being displayed over here, but it's nothing to there's nothing too complicated. Okay, wait. Did I not import something previously? Okay, yeah. So now what's going on is basically it's going through multiple cycles through the data, and it's training the model and trying to minimize the loss that I mentioned earlier. And the loss is determined based on the mean squared error that I previously mentioned. And there are a bunch of other loss functions as well. And but you could check out the documentation for that. So this usually takes a second or two. And over here, 100 is just an arbitrary number. It doesn't the number of epochs definitely does matter, but you shouldn't train it too much because if you have too many epochs, then it would perform it would overfit, which essentially means that it would do extremely well on the trained data, but it wouldn't do as good on the test data because it overfitted for the trained data. But if you we could even try out some other epochs as well. Like, and over here also do note that it shows us the loss, which initially it's much more like over here loss, but then it quickly goes back down. So this also shows that we don't need like 100 epochs, even like lesser epochs would be suitable. So yeah, and if anyone has any questions, do leave it in the chat now and I can get to it later in case. So yeah, okay. Now we're fitting the model and we're basically trying to predict values based on the train and test data. So I run this. This gives us the values that the model predicted basically on the data. But you may have noticed like over here the values are like 0.12, 0.13, and it's extremely small. But that's also because I mentioned earlier that we used the min max scalar over here to normalize the data so that the data is between 0 and 1. So like the all-time high of like the Bitcoin value of like, let's say 65,000 it's normalized, and then it's the output is a value between 0 and 1. So but then once we can reverse the normalization and essentially get it to the pre-scaled values in order to compare them with the original input values. And that's what we'll be doing here. Min-max scalar, which is used to basically reverse the transformation. So now you can see that these values are more like Bitcoin prices. Like so this is the first element, which means like 1,000 days ago it was like 3,500, and then if we scroll down we'll eventually get to like 60K or something. And so now we're also using a metric called the root mean squared error, which basically it tells us like how good the model is performing. But this is a bit more like math oriented, and I'm sure some of you may have like learned this, but it basically represents the square root of the differences between the predicted and the actual values. So over here you can see the train score is like 329.92, and this is like 2000-ish. But the root mean squared error of the train data is usually lesser than the test data because we're training it on the test train data, and then it may perform a bit worse on the test data. But that's expected. But so now we'll be shifting the train predictions for plotting. So what that means is that essentially we're shifting the predictions so that they align with the x-axis and with the original data set. So so that the values correspond with the original data set as well. So then we're doing this for the train data and the test data. So if I run this, then yeah. Okay. So I'll just give you like 2 minutes in case anyone's following along and you're trying to catch up. And let us know if you have any questions again in the chat, so we could hopefully get to them by the end of the workshop. And if you haven't really understood anything, you could ask us, or otherwise if you think that you're overwhelmed by the introduction here, then you shouldn't worry right now, because this is normal if you're starting out right now. But if you've done something like this before, it hopefully isn't too overwhelming for you, and learning, and something that's extremely beneficial about learning this is that even if you don't understand it at the beginning, you could like self-learning this kind of deep learning or like AI or whatever isn't very difficult. Like as opposed to if you're like studying biology or something, I'm sure like self-learning for like a topic like that is much harder. But when it comes to say deep learning, neural networks, there are so many resources online, and we'll be sharing a couple of links with you later and like some YouTube videos and stuff, and you could definitely check them out. Okay. So I'd mentioned that we shift the predictions over here for plotting so that they align with the axes. And we also taken the sequence size into consideration. And over here, we're using some NumPy functions as well. And since most of you are familiar with Python, and if you've used NumPy before, it hopefully isn't too difficult to grasp. So the thing right now is that with the current data, the indices are still like when we essentially plot them, we'd like to have like indexes representing the date. But earlier, if when we were prepping the data, we in fact stripped out the indexes, and so that's what we're doing over here. So what this basically does is it loops between like 0 and 999. Actually between 999 and 0, and what it does is every 100 values it gets the data of that, so that like later if you scroll down and then if you see, okay, the plot isn't here, but when we plot it, we'll be displaying the date on the x-axis at every 100 days, in fact. So instead of displaying like for every instance, it may fill up the x-axis completely instead of and it may be a little too much information. So that's what this is for. So yeah, so that's what this is. We over here where dates.in basically stores the indexes, and then we're appending them into the crypto data, so that when we're plotting them, we'll have that as a reference as well. Now lastly, when we get into the plotting itself, we create a figure size, which is like a 20 by 10, and then we use the matplotlib functions, and then we as I mentioned before, we normalize the data to have a value between 0 and 1, but again we reverse the transformation and we get the values back to its original value so that we can plot them again. And then we plot the trained values, the predicted values in the trained data, along with the predicted values on the test data as well. And we label the y-axis. This is essentially just a label. And then what xtext basically is the location at which we're displaying the ticks as in the labels of the x-axis. So if you think of it as like as the x-axis where the 0, 1, 2, 3, 4 all the way until 1000, at the 0th position, it prints the first element of this, which is the 9th of December. And then in the 999th position, which is the last position, it prints the date of this. Not exactly print, but it labels the x-axis. So if I run this, it shows us a plot, which so over here the blue lines are basically the actual like closing values, and then the orange lines over here are the predicted values in the trained data. And over here, if you've noticed, and the green one are the predicted values in the test data. But if you've noticed over here that the orange lines are almost completely overlapping with the blue ones, and that's because the whole model is trained based on the trained data, which means that it would obviously perform better on the trained data. And then although the test data and the predicted values in the test and the actual closing values, they don't completely overlap because the model is then tested on the test data rather than training it again. So, and it predicts the trends really well, even if it doesn't predict the actual prices. So that's it for the coding portion. But if anyone has any questions, do let us know now, and then I could get to them. So I'll give everyone a couple of minutes in case you have questions with anything. Yeah, if any of you have questions, you can, don't feel shy or anything. It's okay. It's fine. Okay, so if any of you don't, if no one has questions for now, I'd like to show you something else with as I mentioned earlier that if you train it for like too many epochs, you might overfit. So, and over here it's 50. So if I instead do 100 and then I train it, and okay, wait. Oh, I think I have to rerun everything again because yeah. So now if we run it for another 100 epochs, what you might notice is that it'll hopefully show on the graph as well that it would essentially perform too well on the train data, which means that it hasn't like it doesn't reflect well in the test data. So yeah, it's done training. So now if I okay, like even over here, the root mean squared error scores have increased, showing that this would perform worse than when we ran it with 50 epochs. So like over here, although like the difference may seem very minimal, but on a larger scale, it makes a difference. Like for example, in this portion over here, like with the even in the training data, it isn't exactly overlapping in all cases, whereas previously it was. And then even for the test data, there's a little more error over here, but that's because we trained it for too many epochs. And you could even play around with the sequence sizes of like 10, and then like I'll go up again and so over here, right? So like I mentioned before, the sequence size is the number of steps that it looks back. So essentially the next value is predicted based on, like in this case it was the 10 previous values. So over here, if it's 15, But sometimes if the sequence size is too much, then it's basically like too much information, and then it doesn't perform the best. But and too less, on the other hand, could instead be that it doesn't have enough information. So, okay, in fact, over here, the test score is lower than the previous one, which could mean that this performs better on the test data. But yeah, so this performs slightly better, I think, by looking at the graph. But that's just, you could definitely play around with these values, and you could take a look at the notebook and even play around with the number of epochs as well. And just but anyways, if you have any questions, you could let us know now, or we can wrap the session.